Oh, pens are missing. Review from last week. Oh shit, wrong button. Let's try that again. Sorry. Come. Work, please. There we go. All right. So, Calc 2 week, extra line there, 1 review. So the biggest idea we did was calculating an area using a Riemann sum. And a Riemann sum, we use that sigma notation. We have some counting variable. The height of every rectangle comes from plugging in an special x value into a function. And then every rectangle has a width that we call delta x. Right, so that's the big idea. So I'm going to do a specific example of that in just a minute. Before I do that, I want to connect that to the idea of the definite integral. So the, this should be a wavy equal sign, because those rectangles just approximate the area. And the approximation gets better the more rectangles we use, right? The definite integral is actually equal to the area, right? So that's a straight equal sign. And that's written with that funky S, which stands for sum, as your x value goes from some starting value to some ending value. You need to know your function, and that just says the variable is x, right? It's kind of a little redundant, but it's related to that right there. The connection between the Riemann sum and the definite integral comes from taking the limit as n goes to infinity, if we can find that limit. So this is where things get pretty hairy, because we have the limit of the sum of a function. And the hardest part about a Riemann sum, the first hard part is coming up what's the equation for those x values. Okay. Then the next part is, can we simplify the sum? And if we can simplify the sum, can we take the limit? So we're going to do a couple of examples of that, and then we're going to find the easy way, which I threw in at the last 3 minutes of class last time. That's called the fundamental theorem of calculus. So this is a summary of last week. I'm going to do a couple of specific examples of this next. Bottom line is, we're trying to calculate areas. Those areas are approximated with rectangles, right? Wavy equals approximation. If we can figure out how to take a limit, then we can get exact areas. So today what I want to come up to is to come up with is an area related to a parabola. All right, so let's do a super simple example, and then we'll do a harder one. So we're going to let f of x equal 2x. Relatively simple straight line. And the interval we're going to take a look at is the interval from 0 to 1. I'm going to go straight to n subintervals. Instead of saying n is 5 or 10 or 100, we're just going to leave it as n. I prefer to do right-hand endpoints. They're the easiest ones to come up with. For me, left-hand endpoints aren't much harder, but I like right ones. So I'm going to do right intervals, or right endpoints, excuse me, endpoints. And basically, that's all the information I need to start, and then I start building my sum. So to build the sum, I have to build the rectangles. To build the rectangles, I need to know what the width and height of each rectangle is. Well, the width of each rectangle, the base of each rectangle, that's always delta x. And delta x is always the width of the interval. So subtract those two numbers and divide by how many rectangles you want. In this case, n. So my delta x here is just 1 over n. Like last week, we had 1 over 5 pop up. We had 1 over 100 pop up. We did 1 over 10. Height of the triangles comes from plugging some special x value into the function. So I have to find that x value. So the way I usually start is by saying, okay, what's the left endpoint? Well, That's called x0. In this case, it happens to be 0. It could be another number, like 1 or 2 or 5 or pi. Then I jump to the right 1 unit. What do my units look like? Those are the units I'm jumping by. I just keep jumping by delta x each time. So x1 is going to be starting at 0, add a 1 over n to that. Okay? So x1 is just 1 over n. And then I just keep repeating that. What's x2 going to be? Well, it's going to be another one of those. So I now have 2 of those. So I have 2 of those 1 over n's. What's x3 going to look like? 3 of those 1 over n's, and so on. In general, if you use right endpoints, the ith x value is always going to be take the left endpoint, which we usually call a, and then add that 1 over n to it I times. That's always the formula for right endpoints. And it can, if you do it right, be the formula for left endpoints too, we saw last week. So in this case, for me, a is 0, so I can ignore that. So I get 1 over n times I is the formula for my x values that I get to plug into my function. Now every function is different. Sometimes it's squared, sometimes it's a square root, sometimes it's 1 over x. In this case, it's 2x. So the height of my rectangles then, switch color back to black, is going to be 2 times this number right here, right, which we could clean up a little bit. So that's the height of each rectangle. So to get the area, just multiply those two guys together and then start adding them up. So the area here is going to be approximately equal to the sum. Since I'm doing right endpoints, I start at 1, and there's n of them. I usually like to write the height first. So the height, if I clean that up, is 2I over n. Is that right? And the width is just 1 over n. So I'm doing the general case here. Last week we did a whole bunch of these where n was 4, or n was 5, or n was 6, or n was 10, or n was 100. I'm just going to let n be n for now. Now, what's the variable here? I is the variable. Yeah, I is my counter. N is fixed at any instant. Like maybe it's going to be stuck at 5 for a little bit, or maybe it's going to be stuck at 10. Okay, so I is the variable. So I needs to stay right where it is. But as far as the sum is concerned, 2 is a constant, n is a constant, and n is a constant. I can pull those constants out. That's one of our rules of sums we learned last week. So this simplifies a bit. I can pull out the 2, and I can pull out the n's in the denominator, so there's an n squared in the bottom. Then all that's left to add up is what? Just I is the only thing left, which means take 1 plus 2 plus 3 plus 4 plus 5. Don't we have a shortcut formula for that? Yeah. Remember that from last week? So the shortcut formula for this here is n times n plus 1 over 2. This other constant's still chilling out in front, so now I have 2 over n squared out front. I can reduce that a bit, right? So let's see, the 2's cancel, one of the n's cancel, so it looks like it's just n plus 1 over n. When I do my cancellation, 2's divide out. That n goes into n squared n times. Yeah, just n plus 1 over n is all that's left. So that way, if someone said, all right, I need a sum, I need an approximation of the area for 5 rectangles. If I just plug in 5, that would be 6/5 would be the approximation. Somebody says, okay, I need an approximation for 100 rectangles. What would the area be for 100 rectangles? It would be 101 over 1. Okay, so just a note on this, if n was equal to 5, then the area would be approximately 6/5. If n is equal to 100, the area would be approximately 101 over 100, right? Because the formula was n plus 1 over n.
Oh.
Okay. As a decimal, this would be 1.2. As a decimal, this would be 1.01. If I plugged in n equals 1,000, the area would be approximately what? According to that formula? 1,001 over 1,000, which as a decimal would be what?
1.0.
Oh.
1 in 1,000. Does there seem to be as n approaches infinity here, does this area seem to be approaching something?
Yes.
Seems to be approaching 1. So I can take the limit of that sum, can't I? Yeah. So earlier I said the definite integral calculates areas. Technically, it calculates what we call net area. I'll explain that in a minute. And in this case, I started x at 0, I went to 1, right? My function was 2x. And I'm integrating with respect to x. X is my variable. Technically, that equals the limit as n goes to infinity of whatever Riemann sum you came up with. And the Riemann sum I came up with was I went from 1 to n. Let's see, 2I over n was my height, and 1 over n was the width of each rectangle. That's what we started with. However, we were able to whip out some kick-butt algebra on that and simplify that down dramatically so the sum disappeared. What did we find that sum went to?
N plus 1.
N, well, yeah, not the limit. The sum went to n plus 1 over 1. Yeah, so that sum right there turned out to be n plus 1 over n, sorry. Now, I can take the limit of that as n goes to infinity. That's a polynomial divided by a polynomial. Rule is leading coefficients of the highest power of the variable. 1 over 1 is 1. So now I found the net area. The exact area based on this function between 0 and 1 is 1. So let's draw a quick sketch of that to confirm. Here's 0, here's 1. If you plug 0 in there, you get 0. If you plug in 1, you get 2. So there's a graph of y equals 2x from 0 to 1. I'm trying to find that area right there, which is just a triangle, right? Yeah, so some of the homework in 1.3, if you started it, says, hey, can you, what was that 1.2? I think it was 1.3, so find areas using geometry.
No, 1.2.
1.2 asked for that too? Okay. So base is 1, so 1/2 times base. What's the height here? 2, which gives me that same number. Now, problem is we can't always apply geometry to get the area. Okay. So we're going to do a slightly harder problem.
The area is the limit.
The area is the limit of the Riemann sum, correct? Yeah. Yeah, so a definite integral is this. Definite integral is this right here, and it always tells us net area. So a quick note on net area, then we'll do a harder problem.
Oh, is that like how we had to subtract the exponents with the limit way?
That's part of it.
Okay.
Yeah. So consider the function y equals 2x minus 3 for a sec. If I graph that, it has a y-intercept of -3, and then I go up 2 over 1, up 2 over 1. So its graph looks something like that right there. If I wanted to find, say, the area, this intersection here would happen at 1.5. As x goes from 0 to 1.5. What's the height of that triangle?
-3.
Yeah, technically it's -3 because it's going down instead of up. So this sucker has a height of -3 and a base of 1.5. So area of a triangle, that area right there would be 1/2 times the base, I'll rewrite that as 3/2, times the height, -3. So the area there would be -9/4. Okay, so net area means sometimes areas come out negative and sometimes they come out positive. If I was then to integrate or to find an area continuing out here from like 1.5 to 3, what's going to happen over here? That area is going to be positive. Now we have some symmetry going on here. These triangles are the same shape. This triangle right here in black has a base of 1.5 and a height of +3.
0.
So, well, if I put them together, yeah. So if, in terms of net area, if I tried to find the integral as x went from 0 to 3 of this function, 2x minus 3, with respect to x, that answer is going to be 0 because the net area here is negative, the net area there is positive. Their absolute values are the same and they cancel out. So that would be 0. So net area, if you integrate a function and the function jumps around from being positive to negative, areas are going to start canceling themselves out all over the place. There's another idea called total area. And the way total area works is you would have to find any regions where the function is below the axis, like right here, and rewrite them as positive. Okay. So net area is just a straight sum. There's nothing fancy about it. Sometimes you have negative heights, sometimes you have positive heights. Another idea is called total area. And total area is a bit more complicated. You can use the definite integral to find it, as your x values go from wherever to wherever. But the trick is to make all the heights positive, we have to take the absolute value. And pretty much the only way to do that is you pretty much have to graph the function, find all intervals where f of x is less than 0 versus where f of x is greater than 0. And anytime it's less than 0, you got to flip it up, okay, which gets a little messy. And so we'll worry about that later. But there is a distinction between net area and total area. Net area is pretty straightforward. You just use your sums. Total area is trickier. Yeah.
Wait, so like an area in like quadrant 3, would that be positive because the x and y are both negative, or does it not work that way?
Yeah, it does work that way too. No.
Is it just below the
It's
x
just,
axis?
so the bottom line is, as long as x is moving to the right, it's only y that determines whether it's positive or negative.
Okay.
So the quadrant isn't as significant as whether the function is positive or negative.
Okay.
That's what matters.
Okay.
Yeah. There is another twist on that I'll talk about later.
What's that word right there after the x is less than 0?
Versus, yes.
Versus.
Graphics greater than 0. So like with the previous problems for total area, the original function, let's see, 1, 2, 3, 1, 2, 3, 1, 2, 3. The original function I'll do in red, that started here, went up 1 over 1, up 1 over 1. So it looked like that right there. So that's my f of x. What's the absolute value of f of x look like? Well, the absolute value of a positive number stays positive, so that's going to be identical. But then the absolute value of a negative number is positive, so what's going to happen there is it's going to make a V shape. So the blue would be what the absolute value of the function looks like. So the bottom line is, in order to make this happen, you pretty much have to find all zeros determine if the function changes sign on each side, and then any place that it's negative, you gotta flip it positive. And we'll work on that later. I just need to warn you about that. All right, let's do another example of limits, and then we're almost done playing with limits. Let's let f of x equal x squared. And I'm gonna make a quick graph of that off to the side. And I'm only gonna concern myself with the positive part of this graph. So I have a point at 1, 1, I have a point at 2, 4. So this gives me that parabola shape heading up there. And I'm going to add a slight twist to this. I'm going to pick some random number in here. I'm just going to call it b for now. Usually the right endpoint's called b. I'm going to let the starting endpoint be 0, but I'm not going to name b yet.
Is it a straight line or is it?
That's supposed to be a vertical line here. Okay. So I'm trying to find the area going from 0 to some number b to the right. Okay. Yeah. So what I'm trying to do is I'm trying to find the definite integral as x goes from 0 to b of x squared with respect to x. Now, ignoring the fundamental theorem, which I stated briefly last week, I'll come to that next. I have to do a Riemann sum. So I'm going to go for a right endpoint here. With n subintervals. So delta x is always the width of the interval divided by how many rectangles. So what's the width of the interval I'm looking at here?
B.
Yeah, 0 to b is just b. So the width is b. How many rectangles am I going for?
N.
N of them. So in this case, delta x is b over n. Okay, so that's delta x. To get my x sub i's, switch colors for those. We always start. I'm using a right-hand endpoint, so I start with the left side, 0, and then I add on my delta x. What's my delta x again? B over n. And I'm repeatedly adding that. How many times have I done it in this case? I times. So it's b over n times I. And that's always the formula for right endpoints. That cleans up a little bit, right? It's just b times I over n. So now I'm ready to set up my sum. So I'm doing a sum as I goes from 1 to n. How do I find the height of each rectangle? You plug that x value you just found into the function. Okay? So that means I have to square my bi over n. So that's the height of each rectangle. I plug in that crazy x value into my function, and then I multiply by delta x. What's delta x here? B over n. So if you decided you wanted 10 subintervals, you would just replace n with 10. If you wanted b to go with 2, you would just replace b with 2, and you have a sum. But you could do that for 100 or 1,000. You could make b 15 if you want, or 1/2. Right, so we kind of have a general formula for sums, but it's only sums when x is positive. Is it much different when x is negative? It turns out no, it's not. We're going to stay positive. Can I clean this up a bit?
Yes.
Oh yeah. What's my only variable here right now?
I.
I is the only variable at this point in the summation. So everything that's not an I can basically pop out. Okay, so what kind of things are going to pop out? Well, I have a b squared times a b, which is altogether a b cubed. It's to pop out. I have an n squared times an n in the bottom. So I get to pop out a denominator of n cubed. So I'm just going to drop my highlighter in here for a second. I've taken care of this b and that b, this n and that n. The only thing left is the I, which is squared. So those constants pop out. I get I goes from 1 to n of I squared. And we have a formula for that, right? Okay. And on the test, if you need them, I'll give you those formulas for I squared, I cubed. Okay. We have a formula for the sum of the squares. 1 squared plus 2 squared plus 3 squared plus 4 squared. So next page, here's where I'm at. My area is approximately equal to this sum, and the sum is cleaned up to be b cubed over n cubed. The sum of the squares is n times n plus 1 times 2n plus 1 over 6. That's the formula for the sum of the squares from 1 to n.
Yeah.
This cleans up a little bit.
Yes.
Not a lot, but a little.
One end cancels out.
Yeah, one of the ends cancel, and that's kind of about it. So I'm going to get a b cubed times n plus 1 times 2n plus 1
That's from n cubed n squared.
over n squared times 6, 6n squared. Usually I wouldn't bother multiplying that numerator, but I'm going to multiply those binomials together. I'm going to leave the b alone. So if I multiply those out, I'm going to get b cubed times 2n squared plus 3m plus 1 in the numerator. In the denominator, I have a 6n squared. So if you tell me that b is 10, or sorry, n is 10, I can just plug n in there. I don't even have a sum anymore. I just have an algebraic formula for the approximate area. Right? This is approximate at this point. How do I get the exact area?
Take the limit.
Take the limit. Okay. So I'm ready now to get the exact area by taking the limit of this as n gets big. All right, now n is the variable. Just shifted. We got rid of I. Now we focus on n. So let's see. As far as n goes, I just get to focus on this stuff here because the b is a constant. It's not an n. This is a polynomial over a polynomial, right? Rules for limits of quotients of polynomials is if they're the same degree, what happens?
The
The
coefficient.
leading coefficients take over. So that means this limit is basically 2 over 6, which is really
1 over
1/3. So what's the limit here then? Putting it all together,
1/3.
and then we're missing one part?
B.
B cubed. Yes, so it's 1/3 b cubed. Okay. So next I'm going to tell you what all this means, and we're going to find the easy way to do it. So we don't have to do this anymore. Because this is very, 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 very hard. The easy way is like, third is hard. Okay, so back to where we started here. I started with the function f of x equals x squared on the interval from 0 to b. And what I wanted to do is I wanted to find the area using the definite interval. So I went from 0 to b for x squared dx. And after all of that algebraic calculus jiggery-pokery, I found the answer was b cubed over 3. So I've discovered an area function in terms of the endpoint b. The area function is b cubed over 3. Now, back to that picture again. What kind of number is b? Well, it's just an x value, right? So there's no reason I couldn't state that the area function is really a function of x, and it is whatever x is cubed over 3. Okay? So here's my question to you. What is the relationship between x cubed over 3 and x squared? Tyler?
It's the antiderivative.
Yeah, going in this direction, it's an antiderivative.
Well, that's the.
Oh yeah, I lost shit. Oh my.
Chase the derivative.
Going this way, it's the antiderivative. Going the other way is the derivative. So that was my point last week when I stated the fundamental theorem. What the fundamental theorem is a couple of people have been doing calculus for thousands of years, actually, right? Only a couple hundred years ago did someone realize, oh crap, derivatives and integrals are just opposites of each other. So a definite integral, all you need to do them is antiderivatives. And to do antiderivatives, all you need to know how to do is derivatives, and just reverse it. So that's the power. Okay, so I'm going to restate the fundamental theorem, and then we're just going to start using that instead of all of this huge machinery. Okay, Sam, you okay?
Yeah,
You look stoned.
I'm just really sick and tired. Not of this, just of my cold.
So now we're getting to the fundamental theorem of calculus. Because this was a hell of a lot of work. How many pages did that take? 1, 2, 3, okay. 3 pages of hard work. So back to the fundamental theorem of calculus. All right, Ms. Miller, you gonna live? All right, so let's see. That works. So I've got some function, f of x. And f of x is going to go from some number a to some number b. And what I'm concerned about is finding an area function for f of x for this area in here. Just use a highlighter for left. So I'm trying to find this area function. Given some x value here. So then the area function is defined to be the integral, definite integral from a to x. And then since I'm using x as an endpoint, I have to use a different variable inside, otherwise you get confused as to which is which. So we just put a t dt in there for now. So that's my area function right there. So for the previous example we just did, my area function was x cubed over 3. And then the f is called the boundary function. That's the f of x equals x squared that we were playing with on there. So that's what we discovered a moment ago. So what the fundamental theorem of calculus says, the first part of it says basically the area is changing in this situation only because the top is shifting up and down. Right? X is moving to the right, sure. But if this was a straight line, like y equals 2, the area would just increase steadily. But in this case, the area is not going to increase steadily because this function wiggles up and down. So the bottom line is, as x moves, the area inside is entirely dependent on the shape of the top function. So that change in area is a derivative. And I'm talking about the change in area. So part 1 of the fundamental theorem says that the rate of change of the area, A prime, is just that boundary function. Which is like, so what? But the power of this is that if one direction is a derivative, what's the other direction? Antiderivative. Yeah, so that what this implies, so the huge implication here, is that a of x, the original area function, is an, or basically any, antiderivative of the boundary. Antiderivative of f of x. Okay, so that's part of the consequence of part 1, which leads to part 2 of the fundamental theorem. which I can illustrate pretty easily with a picture. So I have some function up here, I have some number a right there, and I have some number b right there. Okay. This region right here, that's the area up to the number a, from 0 to a. This red region would be what? The area from 0 to b. So the red region is the area from 0 to b. If I wanted just the area in between, couldn't I just subtract the blue area from the red area to get that? Yeah. So the area in between would be b's area minus that previous chunk up to the left. Just subtract those two. Okay? That's this yellow area I have in the middle. But we came up with a definition earlier called the definite derivative, the definite integral, that says that area is also the integral from a to b of f of x dx. And this part right here is what we call part 2 of the fundamental theorem of calculus, is that if you can find an antiderivative, that antiderivative can be used as an area function. Okay. So now, once we know that, we don't have to do Riemann sums anymore. Okay. Except one more time on the test. Sorry.
And then bring it up.
All right,
Yeah,
so
final.
what's that?
In the final.
And then one more time on the final. Okay. So aside from that, you almost never need to do Riemann sums again.
On test 2 and test 3, no more Riemann sums.
Yes.
Okay, good.
Unfortunately, I will do some in class in between now and then to illustrate some other cool ideas, like volume and surface area. All right, so let's use it. All right, so let's take a look at a relatively simple example. We're going to go back to f of x equals 2x minus 3. And the interval I want to look at is from 0 to 2. So I'm not going to draw a picture at first. I'm just going to use the fundamental theorem of calculus and then see how it applies to a picture. So if I want to find the area there, that would be the definite integral from 0 to 2 of 2x minus 3 with respect to x. And the fundamental theorem says, can you name an antiderivative? So let's try. So I'm going to put an equals, and then I like to put a square bracket next. So what's an antiderivative for 2x? Antiderivative. So what function would you take the derivative of to get 2x? It'd be x squared, right? That's an antiderivative for 2x. Now, it could also be 2x plus 1 or 2x minus 5. Forget about the constant for now. Fundamental theorem says any antiderivative will work. Doesn't matter which one you pick. All right, so I'm going to put the minus in. What's the antiderivative for a constant?
X.
It would be 3x, right? So that'd be minus 3x. So that's an antiderivative for that whole thing. Are there other possible antiderivatives? Yeah, plus a constant. Forget about the constant. You could throw it in there, but you don't have to. So then what I like to do, once I still have to remind myself to deal with the boundaries. So next I throw my boundaries back in, but on that side. This is the notation you'll see more often. So this is my area function. So first I have to plug in the right endpoint too, and then I plug in the left. So next thing I do is I evaluate that by plugging in a 2. And then I take that away from plugging in a 0. And then I clean it up. Okay, so let's see. 2 squared is 4. Minus 6, and that's all 0. So the area appears to be -2. Now remember, this is, the idea is net area here. So areas can cancel themselves out. So we're going to draw a picture to see if that matches. After that, we're just going to have to believe it works. Okay. So, picture. And I drew this picture earlier, 1, 2, 3, 1, 2, 3, 1, 2, 3. So this has a y-intercept of 3, and then it goes up 1 over 1, oh, sorry, up 2 over 1, up 2 over 1. So there's the graph. Does anybody remember where it crosses at there? Crosses at 1.5 there. The area I'm trying to find is from 0 over to 2, right over there. So I have some area that has a net negative, and I have some area that's a net positive, right? So this one over here has a base of 1.5 and a height of -3, and it's a triangle, right? So I have to cut that in half. That's the area of the first triangle. What can you tell me about the second triangle? It has a base of 0.5 and a height of 1. Cut that in half. All right, so let's clean this up a little bit. Decimals, I hate decimals. I'm going to make these into fractions. So let's see, 1.5 is 3 halves times -3 over 2. And this one would be 1/2 times 1 over 2 with fractions. So that gives me -9/4 plus 1/4. Which equals -8/4. -8/4 is -2. Yeah. So here I've done it using geometry. And there are some problems that say, hey, try to solve these using geometry. Okay. But it turns out we have another tool. We have the end-derivative tool we can use too, if geometry fails to work. All right, and I am out of time. So what I've reviewed here is section 1.1, section 1.2. I've just covered 90% of section 1.3. There's another idea I need to go over more carefully, which is the idea of total area, which involves absolute values, which is messy.
Are we still?
So we'll do that tomorrow. So we're still on track with the current due dates. Yeah, and if hopefully I won't make another due date mistake like I did last week. I apologize for that mistake. But I think we're good for the next couple of days. We'll double check dates tomorrow.
We should be taking the test next Friday.
Yeah. Oh yeah. So the test is scheduled for next Friday. So everyone take a look at this with me here. So remember, we got this handy dandy calendar at the top where I'm predicting when homework should be due. Every once in a while I make a mistake, like I said homework 1-2 to Sunday, but it should have been today. And I think if I'm wrong, please correct me, but anyone that wasn't done on Sunday with their 1-2, I moved your due date to Tuesday for you. If you gave yourself a late pass, I give it back to you. So the exam, I'm hoping we'll be ready for it by Friday. Some of my students online can't get to a testing center on Friday, which means they're going to take it on Monday. To be fair to you all, like last quarter, I give you all the choice. You can get it done that Friday, or you can wait till Monday to get it done. You just need to let me know by next Thursday which way you're going to do it. Just get it done. Don't worry about it over the weekend, or you can have the weekend to study more. Okay? All right, that's it. Take care. Have a good day. Do good math.